Okay, today we're going to continue on with a discussion about relative velocity, and we might throw a little bit of acceleration in there, but I also want to make sure I touch on instantaneous center of zero velocity, which I think you'll find a useful tool to be able to make sure that the work you're doing up here on your vector calculus is correct and you're on the right track. Okay, so it gets some additional insight by knowing something about this instantaneous center. So what you want to remember from the last session is if you have a rigid body with a couple of points on it, then the velocity of one of those points as a vector, imagine you're looking at these from a reference point and you're actually an observer, let's say at a location here, B. Then the velocity of this point is going to be equal to the velocity of point B, if that's known information, plus the relative velocity. In other words, how is A moving relative to B? Now, you know that if this is a rigid body, I said this last week, if this is a rigid body and you're looking at this velocity of A relative to B, and this body has some angular velocity, omega, and let me go ahead and give it the vector symbol as well, then how must A be moving relative to B? What type of physical motion must be occurring of A relative to B? Only in rotation, if this is a rigid body. So what I did to emphasize that the other day is I used color to emphasize that the relative motion is on a circular path about the observer. So by knowing that, then you're able to remember that this equation then becomes omega cross r of A relative to B. Okay. So that's where we left it the other day. Now, just to summarize where we went just on the theory without doing any practical problems with it, is we then differentiated this last class session. And we came up with the acceleration. And so without going back through the derivation of it, it's relatively straightforward that the acceleration of A has to be equal to whatever the acceleration of B might be, plus then the time derivative of this cross product. And what that yielded was omega cross r of A relative to B, plus alpha cross r of A relative to B. This term is a pseudo, I call it a pseudo normal acceleration term because it's not really a normal regarding the path. It's pointing which way? Omega cross r of A relative to B. Which way is this term pointing? It's got units of r omega squared, which clues you in on which way it's pointing from earlier material in the course. Remember the derivative of this information right here, the derivative of this is where these two terms are coming from. So with the orange arc, that's the apparent path of A relative to the observer here at B. So this one pointing back towards B has to be that r omega squared type of term. This one. And the possibility exists for a tangential one if there is some alpha here also. If there's some alpha, then there could be an alpha term there's the alpha cross r of A relative to B term right there, which is your pseudo-tangential type of term. Okay, so that's the theory for the kinematics on a rigid body. Okay. So let's go ahead and go back to a problem that we left off with last class session, which should show up here on the overhead. And it's this one right up here. We got through a good portion of this problem, and what we were trying to do there was figure out the velocity of point A, its magnitude, and then we also wanted to show that the velocity of A is perpendicular to the velocity of B. So we'll go ahead and put this back up. This is question 67 on page 364. So point B was up here, and point A is down over here. And this is on a rolling, non-slipping rolling surface where this is angle theta. This is the center of the wheel, and it's moving to the right with some velocity of the center of the wheel. And when we discussed the cycloid's motion the other day, we know that the arc that's laid down on the track or lifted off the track, the speed at which that arc is being laid down is the speed of the center of the wheel. So you know the speed of the center of the wheel is what value? If this wheel is rolling with some omega. Okay. So that's the speed of the wheel, center of the wheel. And what we did the other day is we know that the path of this point A is what? What's the path followed by point A?
Absolutely, it's sort of
It's up and moving forward, isn't it? It's that cycloidal path. So point A's path is going to be something like that. And it's going to be carrying some velocity, something like this. So thinking back to the discussion we had previously about the motion of a cycloid, a point on the edge of a wheel, the path being followed is called a cycloid. The points lift off and arc forward. Now what about point B up here? Yeah, it's already past the peak, and so it's coming down off of its cycloidal top, its top of its path, somewhere back up in here. So here's the top of its path, and so it's moving down something like that. Now, it actually is going to have to be, they told us that what we have to demonstrate is what? About the velocity of A and the velocity of B. Demonstrate that they are perpendicular to one another. Demonstrate that they're perpendicular to one another. So just to give us a taste of where we're going with this is we've got to show that the velocity of A is perpendicular to the velocity of B. Okay. So how did we develop the velocity of A the other day without looking back in your notes? Let's just, we're going to use our equation, our governing equation over here. which was the velocity of a point is equal to the velocity of another point plus the relative velocity. So back on here, we're looking for the velocity of A, and that's equal to the what is something that we do know on here.
The center.
Yeah, we know the velocity of that center point plus the omega of this rigid body crossed with r of A relative to O. So this is what we developed the other day. That's going to be your expression for your velocity of A. And thank you. I need to put a k hat on here. And I should probably put a negative if I use the traditional coordinate system. And I think what I'm going to do, see, I have that rolling clockwise, and if I'm using the traditional x, y, the head of the arrow z coming out towards us, then clockwise is into the board, so I'm going to assign a negative omega k to that velocity, angular velocity vector. Right? So we had this the other day. We'll go ahead and put the details in here in just a second. But next to it, let's go ahead and see what the distinction is if we start working up the point on the opposite side of the diameter at the same time. So the velocity of point B is going to be made up of the velocity of the center plus, again, the negative omega k hat crossed with r of B relative to O. And we can go ahead and put those parts together now. So the velocity of A is equal to r omega I hat for the velocity of the center. And then when we do this, we need to write that detail down one more time. But our position vector this time is made up of this magnitude, which is the radius, times the position vector of A relative to O. And so that's to the left by the sine of theta, I hat, and down below the center, remember it's A relative to O, so you're the observer here at the center. Then you're looking at A. So you go down cosine minus cosine theta j. Paralleling that over here with a velocity of B, it's made up of r omega I plus negative omega k hat crossed with now the position vector of B relative to O, which has a positive x component, which is the sine of theta, and a positive y component, which is the cosine of theta. Everybody comfortable? Any questions? Okay, we're just working up the details. What we should see when we finally get done with these vectors of A and B is we should see a pretty steep vector for VA. In other words, a relatively small, at least for small theta, a relatively small x component for VA and a fairly large y component. And we should see something over here for VB that has a large x component and a relatively small y component, just by looking at the geometry, if theta is small, as shown in the picture. So, if I collect the I terms, now, here's my r omega I, the center of the wheel's motion, and then my other I term is going to come from what over here on my cross products? How are you going to get an I term when you're doing a cross product? with a K and IJs.
J cross K.
Or K cross J. K cross J. If you take K coming out of the board towards you, coming out towards us, and you cross that with J, you get negative I. K cross J with your right hand, K out of the board, crossed with J, gives your thumb pointing to the left. Now watch out for the signs here. So the velocity of A then is going to have an R omega term in it, and then K cross J is negative I times a negative times a negative. 3 negatives keep it negative, so it's minus R omega cosine theta, and that's the collection of our I terms. K cross I, K is coming out of the board towards you, and you cross that with I, and you get K cross I gives you J. So we're going to take K cross I, gives you J, and then a pair of negatives make it positive. So we end up with a positive R omega sine theta J term. So here's the velocity. And they wanted the speed, I believe. Is that right? Okay, they wanted the speed of this. So, in the question, the first part of the question was find an expression for the velocity of A, yeah, the speed. So the speed then is going to be the square root of the sum of the squares of these terms. Now notice that there's a common R omega that's going to be involved squared up inside the radical. So R omega is going to pop out of the radical, and you're going to be left with 1 minus cosine theta being squared plus sine squared theta. And when you multiply out the binomial, that's 1 minus twice cos theta plus cos squared theta plus sine squared theta is 1. And so you end up with a 2, square root of 2 factor there. And then that's where we left off on Friday, or last class session. So this was R omega, and we had a radical of 2 minus 2 cosine theta. And we clean that up, and it turns into using the trig identity, twice R omega sine of half the angle. For the speed of A. Yeah.
Under VB, under up above it, just boxes. So there's supposed to be an R in front of your sine theta I plus cosine
Probably, yep. Yeah, there should be.
Should be in front of the parentheses.
Yeah, because this is a radial distance from B to O, from O towards B. And so right here on that unit vector, there needs to be a R value tucked in right there. Thank you, John. There's an R right in there. Good. Everybody fix that? If you're taking notes. Okay, now, back to what I really wanted to get at was show that the velocity of A is perpendicular to the velocity of B. What's the magnitude of the velocity of O? What's the velocity, the relative velocity of A relative to O? The relative velocity, the magnitude of this cross product. It's R omega also, isn't it? Isn't this cross product term right here going to be R omega in magnitude also?
Yes.
So that means both of these components making up the velocity of A are equal in value, just happen to be in different directions. So if we thought about that, we could draw the velocity of O as R omega, being the velocity of O, horizontal to the right. And we could add to it a relative velocity vector, r omega in value, that points which way? Which way is this thing pointing? This thing I have my fingers on.
The direction of that cross product.
Left and up.
goes with theta.
Okay, can you be a little more precise?
Should be pointing to the motion.
Okay, we got to get a handle. What direction is that? What direction is this cross product pointing? Think about what it is.
Negative sine theta I hat.
Okay, can you be a little simpler about it?
Just
Well,
over the path.
to the left and up. I mean,
Well, that's cool. Okay. In other words,
it's
tangential to the circle at that instant. See, the velocity of this point A is made up of that VO, and this. And they're equal in value. And so this angle, what's this angle make with the horizontal? What's this relative velocity make, relative velocity value or magnitude make with the horizontal? What direction?
theta plus
It's theta, isn't it?
dimensional.
Isn't it just theta off the left? Isn't it just up off of here by
yeah.
theta?
Mhm.
Up off of this left-facing axis by theta. So I've got VO. I'm trying to figure out this thing. I'm trying to add this to that. I want to add these together. So what I'm going to do is I'm going to come over here and I'm going to add a vector that's equal in value pointing at angle theta up this way. And it's going to come about that far. R omega, and that's going to be the relative velocity. In other words, the velocity of A relative to O. They're equal in magnitude, making that triangle isosceles. And so that means the velocity of A then is, we'll find out today if this stuff erases off this board very easily. Here it sits. There's the velocity of A that we've drawn over here. Okay. You want to make sure in the problems that you're doing for homework that you definitely can crank out the vector algebra, but you also want to try to have another way of seeing it. Very important. So there's velocity of A sitting there. Let's now use that thinking to talk about the velocity of B. You know, without me going through and working up all the detail. We'll get the detail in a minute. But let's use this graphical thinking to see if we can figure out the velocity of B and see if we can then illustrate why velocity of A is perpendicular to velocity of B. Okay. So once again, velocity of B now is made up of the velocity of the center, which we can draw. Its magnitude being r omega. And now we're going to add this cross product. And remember what this is? This is the velocity of B relative to point O. That cross product. And that's pointing which way?
Theta from the horizontal down.
Okay, and so that relative velocity, I'll use the way I did this before. It is tangent to the circle. Now, not the cycloid's path, but it's tangent to the circle and pointing down that way. At angle theta below the horizontal. Angle theta below the horizontal because this is angle theta off the vertical. And they're perpendicular to one another. Okay? So we're going to come off the horizontal by angle theta, and we're going to go down this way, r omega in magnitude, and that's the velocity of B relative to O, this cross products term. Now I'm just going to reset where I have these two identifiers because our diagonal here is this velocity of B. Okay. So there's r omega. That happens to be the magnitude of the velocity of the center of the wheel. And then we end up with this thing in orange being the velocity of B. So does that demonstrate to us that these are perpendicular from this nice picture? Visually, kind of. And angle theta sits right over here. They're looking pretty good, aren't they? So are we done? Not quite. Okay. Not quite. And does that make sense to you folks? Down here for small theta, that you're on your cycloid's path, like when we started the discussion about that points initially down here with zero velocity, and it picks up velocity as it comes up. And then when it's up here near the top, it's really moving. And so that's why you should see a distinct difference in these magnitudes clearly here. That should feel right to you. Okay. So we want to do more than just nice little graphics here. We want to do it mathematically. If you look at this picture, can you write down the final result for the velocity of B similar to what we did here for the velocity of A? Look how easy it is. The velocity of B vector, by looking at this picture, compared to coming down here and playing the cross product game, is the velocity of B is going to be made up of an I component, which is r omega, plus the horizontal part of this guy, which is r omega cosine theta. And the j component is downward, and the only part of it is due to this. It happens to be minus r omega sine theta j. So there is the result of the vector algebra for the velocity of B from the graphics. Make sense? Okay. So we have the velocity of A down here. We have the velocity of B over here. How are we going to show that one's perpendicular to the other?
Dot product.
Oh, dot product should be, if they're perpendicular, zero, right? Cool. Okay. So the velocity of A, excuse me?